Okay, so this week focusing on thermodynamics. Thermodynamics is something you're familiar with from your first semester course and also probably from physics courses in high school. We're going to focus in on some other thermodynamic quantities that are important for chemical systems. We're going to start by reviewing what you know from your first semester. If any of this is a little bit fuzzy, you can go back and look at those notes, look at example problems you've done with your professor in your first semester course that dealt with enthalpy, because a lot of the things that we can do with enthalpy, we can also do with the other two thermodynamic quantities we're going to introduce in this chapter. And this chapter, while it's geared towards chemical systems, the stuff that we talk about, every scientist should be aware of and every scientist should be able to handle. So there are like universal applications with the things that we talk about. Just a quick little review of information from last semester. Thermodynamics deals with the motion of energy. So we're going to be making physical changes, chemical changes, and we're going to see what energy changes accompany those. Okay. Last semester we focused in on enthalpy. Now, the reason that enthalpy is so important for us as chemists is because its strict definition is that it's the heat that flows under isobaric conditions. Heat is a type of energy that flows to nullify temperature differences. Isobaric conditions means constant pressure. Now, for chemists, a lot of the times we run reactions open to the atmosphere. So we're assuming that the atmosphere has a certain pressure and that pressure is unchanged. It's isobaric. So if I understand the enthalpy of a reaction, I know the heat of that reaction or how much energy it's generating or taking in, endothermic and exothermic. All right. Concepts that we've already saw when we were looking at potential energy reaction coordinate diagrams, and we're going to go over that quickly again in a bit. All right. Enthalpy, all right, is given the symbol delta H. It is a state function. And in fact, anything we can write with a little delta is a state function. State functions are important in thermodynamics because they are properties that depend on the initial and final states and not the path that links those states. It's not how a change is made. It's just where you start and where you finish that matter, okay? And like I said, we're going to look at two other state functions, two other thermodynamic properties that are also state functions. So the things that we learned about enthalpy in terms of how it behaves from a mathematical standpoint in the context of Hess's law, or in the context of using a table of delta formation H naughts to be able to infer information about enthalpy from other enthalpies. All that applies to these other functions that we're going to introduce this chapter. So if you can review and understand this sort of mathematics that you went over already, some of the problems this chapter are doing it, all right, but for different functions, like doing the exact same thing, doing a Hess's law type problem or a delta formation H naught type problem, okay? In terms of just keeping on with the review, I will remind you, because it becomes important as we analyze things, this superscript 0 here, we say the word not. It implies standard conditions. Standard conditions are monitored at 1 bar for all gases and 1 molar concentrations for anything that's aqueous. And that becomes important because we'll actually be dealing with a little bit of non-standard conditions as well, okay? You'll see your book will mention, and I'm going to point this out here too, that 1 bar is really close to 1 atmosphere. So when we think about standard conditions, they're not exactly the same, and 1 bar is the true definition, but we might use atmospheres in place of bars just because we're so used to using those units in terms of a pressure unit, okay? So you're, like I said, just avoid the confusion. 1 bar is the real definition, but if you see 1 atmosphere is related to standard conditions, it's close enough, okay? I just want to bring this up again because we are going to have to see it in a couple different contexts already. Remember these delta formation H naughts, they're in a big table, and what you did last semester with enthalpy, you'll be able to do with these thermodynamic quantities that we're introducing this chapter as well. And the thing about these delta formation H naughts and using that table is they were super powerful because you could go ahead and you could write, all right, delta H naught for your reaction. So you could look at any reaction and using that table, you could figure out the change in enthalpy, all right, under standard conditions. Incredibly important bits of information, incredibly important descriptor of the energetic behavior of that system. And what you did for those sorts of calculations, because it was a state function, right, is you were able to take a sum, right, over the stoichiometric coefficient times the delta formation H naughts from that table, right? You did a sum, and this subscript I just means for all the products. So it's a sum over all your products. You did another sum, and it looked almost exactly the same, except this sum, and I'm going to use the subscript J just to kind of indicate that it is slightly different. You still looked at your table. You looked at your delta formation H naughts, but you did the exact same sum for your reactants, right? So hopefully this is ringing a bell. You remember doing this, right? If you subtracted those two, you did the product sum, and then you subtracted the reactant sum, right? You got your delta H for that reaction. I know I mentioned it briefly, but just to make sure, this would be the stoichiometric coefficient associated with species I on the product side of the reactant or reaction. This would be the stoichiometric coefficient that's associated with species J on the reactant side, right, of your chemical reaction that you're looking at. And then these guys come from your table, okay? So it's important to remember all this stuff. I went over it real briefly, but again, it's going to be math that you'll have to do again. So going back and looking at those notes is going to be really helpful just to kind of get up to speed with some of the calculations we're going to be referencing this chapter with other thermodynamic properties. All right. One other thing I'll remind you of is that we talked about enthalpy from the standpoint of potential energy reaction coordinate diagrams. And because we're doing things at a constant pressure, okay, we could find enthalpy changes on these sorts of graphs, okay? And remember, we can look at the difference, the starting energy and the ending energy, okay? And that value right here is delta H. This is a potential energy reaction coordinate diagram where energy is released. Energy is released, that means that this is exothermic. The two other state functions we'll talk about, you can have the same ideas in your head, okay? If we're monitoring other thermodynamic properties on this axis instead of just total energy, which is going to be represented as enthalpy for most of our reactions, okay? The idea that the initial and final states is all you need to determine the change, right, is important. We even talked about catalysis, okay? If I have a catalyzed pathway in here that effectively lowers the activation energy, did delta H change? Well, no, it didn't change. So this shows that delta H is a state function. Whether I go over this big hump or whether I go over this small hump, going from my reactants to my products, right? No matter which pathway I take, that difference is always the same, right? So then it's a state function, then these sorts of calculations apply, then Hess's law type calculations apply, okay? Enthalpy's in what we call first law territory. So the last thing in our review section here is I'll remind you about the first law of thermodynamics. And I kind of mentioned it. Enthalpy is seen as the energy of reactions. That's because most of the energy changes can be encapsulated inside that enthalpy for a large set of reactions. So if you want to think about enthalpy as an energy for this chapter, it's okay, all right? First law of thermodynamics was energy conservation. All right, so essentially energy cannot be created or destroyed, all right, in a chemical process, right, or a physical process. Energy conservation is broken for nuclear processes, but we're not really going to talk about these this semester. This is an incomplete picture, okay? So just, okay, if you have energy before and energy after, they have to kind of be equal to each other. The first law of thermodynamics doesn't really tell us enough about how systems behave. We made a lot of arguments based off the first law of thermodynamics. We like to say, okay, things roll downhill, all right? Which means that from an energy standpoint, okay, they like to get to lower energy states. They like to release their energy. How does that fit in with energy conservation? Well, if they're releasing their energy and they're getting to this lower state, if you look at the amount of energy they released and you look at where they are now, you didn't lose any energy, all right? But in the first semester, we kind of make arguments in terms of things rolling downhill. things like to release energy to get to a lower state of energy. And that's not always true, all right? And so we're going to sort of expand on this now. We're going to switch gears. We're not going to be talking about review next, all right? We're going to need to talk about the other laws of thermodynamics to actually talk about what actually happens for chemical systems and other physical systems, okay? You can roll uphill, right? That's possible, right? And that can happen spontaneously. And that's encapsulated by what's known as the second law of thermodynamics. So we're going to try to get a more clear picture on how energy flows in systems, all right? And again, we'll focus on chemical systems. So here's the second law of thermodynamics, something you probably saw before, all right? But again, important for us to go over and to treat like you haven't seen it before. All right, for a spontaneous process, the entropy, not enthalpy, but entropy, the entropy of the universe increases. And what this means is the universe is essentially getting more and more disordered. Spontaneous means it'll just happen, right? That is able to occur, right? Entropy is something we're going to need to talk about. We're going to spend a good chunk of this chapter talking about entropy, right? So we like to make arguments in the first semester course saying things roll downhill, but that's not always the case. What really directs where things roll, how a process proceeds, whether it's going to happen or not, it's all about the entropy of the universe. It's all about the entropy of the universe. So while we introduce the second law, let's talk about entropy. Now here's the thing. We have to remember that the second law focuses in on the entropy of the universe, right? Chemical systems have entropy. Everything has entropy. It's just that the important, all right, entropy is the entropy of the universe, all right? So you have to have some distinctions here, all right? What we like to do is we like to say, okay, delta S, which is the symbol for entropy, right? S is the symbol for entropy. This is an entropy change. When I talk about entropy changes, right, I have to be real specific. Whenever I use a subscript U, that's our important entropy. That's the entropy that decides whether something's going to happen or not. That subscript U means universe. So delta S for the universe, right, is what's going to dictate whether something happens. And you have to get an increase, right, via the second law of thermodynamics. This has to be positive. You have to get an increase in a change in entropy, all right, increase in entropy, a positive change for us to have a spontaneous process, all right. Delta S of the universe looks like delta S plus delta S SURR, okay? So what is this complicated, confusing equation? Delta S, whenever it doesn't have a subscript, is the entropy for a chemical system. And we spend a lot of time talking about it, but the reason I'm bringing this up now is this entropy, it's an important entropy, but it's not the entropy that tells us whether something happens or not. And I'm just going to say it one more time because it's so important. We're going to be looking at delta S's for our chemical systems, right? And we'll know that they're for our chemical systems because they don't have a subscript. They do give us information, but they don't tell us whether something's going to happen or not. Only delta S of the universe, right, is in the second law of thermodynamics, and only delta S of the universe, right, dictates whether we're going to have a spontaneous process or not. For our chemical systems, though, the universe can be broken into our chemical system and everything else. So delta S SURR stands for delta S of the surroundings. And that's why this information is important. That's why it does tell us something about delta SU, but it's not the whole picture. To talk about whether something happens or not, we need to not only understand delta S for our system, but we need to know delta S for our surroundings. Okay, so a real important concept that we are going to focus in on chemical systems now for a bit, and just remind yourself that it's not the entropy. It does give us important information. All right, we're going to talk about physically about what it means, but delta S for the universe is the only thing that ties to the second law of thermodynamics. All right. So what is entropy from a physical standpoint? When we analyze our chemical systems and we try to come up with delta S for our system so that we can maybe feed it into this equation, right, and figure out delta SU, okay? When we look at delta S for our system, what this measures, right, are changes in disorder. S measures disorder. It doesn't measure order, it measures disorder. Okay? So when you hear that word entropy, right, a measure of disorder has to pop into your head. Okay? So entropy measures disorder. Okay? So back to the second law real quick. The second law says that delta S for the universe, for something to happen, the disorder of the universe has to be going up. We're going to now focus in on delta S's for our systems. And once we figure those out and get a handle on them, we can talk about delta S for our surroundings. And then once we figure out that, then we know whether something's going to happen or not. So I know I'm going through this slowly and I'm taking my time and I'm repeating things, but it's a real important idea. So let's talk about delta S's for chemical systems, disorder. The disorder of chemical systems can be inferred via physical arguments. Okay? So just for a quick little example, we kind of have a sense of what disorder means. And one thing we have to be cognizant of is that we have an intrinsic understanding of physical changes. And those intrinsic understanding, understanding of physical changes, that just sort of natural idea that we understand what the physical properties of substances look like under different states of matter, is a good sort of foundation for understanding entropy, right? If you look at order, right, for a solid, liquid, and gas, way back in the first semester, we know solids are close-packed, strong molecular interactions, all closely together, forming crystals sometimes, all right? Solids are really ordered, all right? So when I think about the order here, this order here is big. Gases are almost completely disordered. They're not feeling each other much at all. They're floating around in a big box. They have really weak molecular interactions, all right? If you look at what happens to order here, all right, as we go from a solid to a liquid to a gas, all right, order goes down, right? We would say that solids have a high order. We would say that gases have a low order. Entropy is the opposite of that. Remember that entropy measures disorder, okay? So just based off of our understanding of how solids and liquids and gases look from a physical standpoint, all right, the entropy of a solid is low. We say they have a low S. And if you think about what happens, to go from a solid to a liquid, you actually have to increase disorder, right? You have to increase disorder. You have to get the solid, which is in its nice structural form, to break down. You have to get motion there, okay? And then as you increase that and you go from even to a liquid to a gas, where you have to take those particles that feel each other and you have to make them move as much, we have to make them move to the point where they can't feel each other as much to hold each other in a liquid state, to develop a vapor pressure to then fly away, right? Your disorder is increasing, okay? So solids have a low entropy because they have a high order, okay? Gases have a high entropy because they have a low order. The disorder of solids is small, all right? The disorder of gases is large, all right? And I brought up a really important point even in that discussion, all right? What changes, all right, to go from, all right, high order to low order? What changes inside here can we enact to go from a low entropy to a high entropy? What we do is we have to add motion. All right. So when we focus in on chemical systems and the entropy of chemical systems, right, what we have to remember is motion is intrinsically tied to entropy, right? So then how do we actually kind of look at motion? How do we change a solid to a liquid to gas? How do we put more motion into that system? What we do is we apply a heat, right? So that we can take the temperature and the average kinetic energy and we can raise it, right, to go from a solid to a liquid to gas. So all these components tie together and you kind of need this clear picture in your head, okay? Entropy is about disorder. It's tied to heat and it's tied to temperature because it has to deal with motion, right? Disorder of chemical systems. So this is like referencing a physical process, but everything that we say here applies to your understanding of entropy in general, right? High order is low entropy, okay? Low order is high entropy. And how do we go from low entropy to high entropy? Raise the temperature by applying heat, which adds motion to the system. And motion means more disorder, right? The more motion, the more disorder. Okay, so this is it for like our first little video here. A little bit of thermodynamics review and then a little bit of an introduction to entropy as a concept. We're going to spend the whole next video kind of talking about entropy just in a lot more detail, okay? But understanding this and just in general is definitely going to smooth the transition into the later videos of this week. So try to digest this as much as you can, please.